So in class today, we'll talk about reducing representations in different point groups and just do some practice examples. After that, we might move on to cyclic groups. Are there any questions from the class before we start on anything? Yes?
So for all the characters of the E, why don't we ever use that -1?
In some groups, it does appear.
Can
So,
we do that in the previous example? Then?
which example?
So the previous example, like C2B, C3B, instead of introducing 2, can we keep -1 in the place of 2?
So are you talking about an irreducible representation?
Yeah.
Okay. So if you just take a look at your character tables, right? So the C3B point group, you have the two-dimensional representation E with the characters 2, -1, 0. So that's an example where you see -1.
So can we put -1 in the place of 2?
Well, 1, there's no such thing as a negative integer for the dimensionality of a representation. So we always see positive integers under the class E, right? So you just see 1s, 2s, 3s, and so on. And for any E representation, it's an E because it's first and foremost a two-dimensional representation, so we call those E representations just by convention. Is there something else to that question that to expand on? Okay. Yep. 4.2. Okay.
I want to know the transformation of C2 prime.
The transformation of C2 prime. Okay. Well, let's see if we can figure that out. And we could just work this out for X, Y, Z. So for the point group O, so let's get our character table and just make sure we have all of the symmetry operations for that group. So for O, you have E8 C3s, 3 C2s, which are equal to C2 4s, and then we have 6 C4s, and 6 C2. So you're talking about these C2s here? Okay. So what are the matrices for those C2s if you use X, Y, Z as a basis, let's say? All right, so the C2s, this is a cubic group. So if we imagine a cube, for example, here's the center of the cube, let's say. Those C2s will contain edge centers like this. So we have 12 edges of the cube. Any one of those C2 axes passes through 2 opposite edges, so there should be 6, right? And to write the transformation matrices, we can label each one of those C2s so that we understand their orientations in our Cartesian coordinate space. So we call that X, Y goes back, Z goes up. Then if we call this one C2A, then the transformation matrix for C2A, it would take X to -Y, and it will take Y to let's draw it like this so it's easier for me to understand it. So X goes to -Y, Y goes to -X, and and then Z will go to negative Z, right? So for the character, that matrix equals -1, right? So that C2A, you can draw another C2 that's perpendicular to Z that goes like this, and you can call that one C2B, for example, right? In that transformation matrix, you see X goes to Y, Y goes to X, and Z goes to its negative. So you will always see two of these Cartesian coordinates kind of exchanging, either to the positive or negative of the other. And then the other coordinate that remains on itself goes to its negative. It's different combinations of these, right? So if I look through the x-axis and draw y and z, I can draw two more C2s. One of them we can call C2C, which y and z exchange. So I have 0, 0, 1 and 0, 1, 0. And x will go to its negative. So always the character is -1. If I take the other C2 perpendicular to x, then you can see that y will go to negative z, x goes to its negative, and then z will go to -y. Right? And then you have two others of this form. So always the character is -1. Does that make sense? You want me to do the other two, or you're good? Okay. Okay. So that's how you get the character for the representation. And if you look in your character table, you'll see that the T1 representation, for which x, y, and z are a basis, because you see that on the right side of the character table, under the 6C2 class, the character is -1. So you can check your work and verify that you've got a rigorous solution to your problem. Does that make sense? All right, any other questions? I didn't assign problem, which one was it? 4.3, but if you want more practice doing things like this, you can look at problem 4.3, working out the transformation matrices, and even if you wanted to try a similarity transform, it's time consuming. So I think you see the similar type of work in this problem, but if you just want more example problem to work on, you can use that. All right, so let's construct some different representations and different point groups, and then learn and deconstruct those to irreducible representations. And we'll do a few examples until you feel kind of bored of it and you say, yep, I get it, and then we can move on. If you're not getting it, we can work on it more, or if you want to do that individually, I'd be happy to do that. So let's start with something like this. What is the point group for that object, an isosceles triangle? C2V. Okay. And so for C2V, you have E, C2, sigma C, sigma YZ. Now let's make a representation using say, these two lengths, here and here, as a basis for the representation. So the two long edges of this isosceles triangle will be the basis for a representation. All right? And it'll be a two-dimensional representation because you've got side A and side B, let's say. All right? And we can use this as a basis because side A and B can be related by symmetry. We can see that they're related by the mirror plane here, the mirror plane here, a C2 and E. So that can be a basis. So it'll be basis for a two-dimensional representation. If I perform the C2, A goes to B and B goes to A. They go to the other position, and they each contribute 0 to the overall character. If I were to express that in the transformation matrix form, then I would have 0, 1, 1, 0, character equals 0. Great. If I have the sigma xz, and we'll say that's the plane of this isosceles triangle, the character is 2 because A remains on itself and B remains on itself. And if I take sigma yz, I should get this transformation matrix, character is 0. Okay, does that make sense? All right. So this is clearly not one of the irreducible representations in the point group C2V. So it's a reducible representation. We need to use the reduction formula and decompose that to irreducible representations. So we're just going. We note that there are 4 irreducible representations in C2V, and so you'll do the work of multiplying the character in your reducible representation with the character of the IR that you're testing with the order of the class. Right? So let's see if there are any A1 representations within this reducible representation. So for A1, the characters are all positive 1. So we take 2 times 1 times 1 for the order of the class, plus 0 times 1 for the character in the A1 representation, times the order of the class, plus 2 times the character in the A1 representation, times the order of the class, plus 0. Anytime you see a 0, you can just forget it. It's 0, but 0 times the order of the class times the character of the A1 representation. And that's equal to 4. And then the order of the group is 4, so we divide this by H. So we know that there is an A1 representation, irreducible representation, in this one. Okay? And then the next one, A2, the characters are 1, 1, minus 1, minus 1. So we have 2 times 1 times 1, plus 0 times 1 times 1, plus 2 times minus 1 times 1, plus 0 times minus 1 times 1. Character of the first representation, character of the second representation, order of the class. Add that together, we get 0. So there are no A2s within this reducible representation. Right, go to B1. We have the characters of B1 are 1, minus 1, 1, minus 1. So we have 2, 1, 1 here. 0, minus 1, 1. And then we have 2, 1, 1 here. Plus 0, minus 1, 1. So we have a sum of 4. Then we want to divide by the order of the group, and we get 1. So that means there is a B1 representation. Anytime you decompose the reducible representation to its IRs, the dimensionality of all of those IRs must equal the starting dimensionality of the reducible representation. Otherwise, you've crossed dimensions, I guess. Something wrong has happened. So that dimensionality must equal these dimensionalities added up. Does that make sense? Now that we see that we have a two-dimensional IR that broke up into two one-dimensional IRs, we can stop. But if you wanted to check just for purposes of checking or being complete or something like that, you could always go on and work out the B2. It should equal 0. The characters for B2 are 1, minus 1, minus 1, 1. So we get 2, 1, 1, plus 0 times minus 1 times 1, plus 2 times minus 1 times 1, plus 0 times 1 times 1 equals 0. So as expected, there are no B2s. All right? So we constructed a representation in a point group using some basis to generate matrices. So we have the characters of the reducible representation. We note that it is not one of the IRs in the point group, so we use a reduction formula to decompose to its component irreducible representations. Okay? And so to give you a little bit of a visual, I guess, what would this look like? You would have two components. The fully symmetric case where you have A plus B. So both of these are sort of like in phase with one another. And then the B1 representation would be like A minus B, where the two parts are out of phase to one another. So maybe something like this. Right? So you can see with the C2 and the sigma YZ, one goes to the other. So they would be sort of like opposite to one another. All right, any questions on that? All right, let's work another one. So we can go three-dimensional now. Let's take a pyramid. So it's a tall pyramid, and we'll say each of the three faces on the top are the same. They're same face, same dimensions, but they're different from the bottom face. You can say the bottom face is an equilateral triangle. And then you have some isosceles triangles on the faces here. Isosceles. I don't know how you spell that. Triangle faces. And they're equal. What's the point group of this object? It's C3. We have E 2C3 and 3 sigma V, right? So let's take, maybe we have 3 people visiting along the base, and they were interested in standing at those corners. Or we could just take the 3 corners at the base as a basis for a representation. Base, corners. And since there are 3 points, right? This will be the basis for a 3-dimensional representation. Okay? Now notice if I take a C3, each point rotates to some other point. Right? And so they contribute 0 to the character. When I write the matrix, the transformation matrix, there are no diagonal terms. Right? So if I have A, B, and C here, and I do a C3, A goes to B, B goes to C, C goes to A, for example. And the transformation matrix has no ones on the diagonal. So A goes to B, right? The 1 is off diagonal. B goes to C, the 1 is off diagonal. C goes to A, the 1 is off diagonal. So we have a character here of 0. You can either work that out with a transformation matrix, or you might even start to get in the habit for easier examples where you can just sort of realize if one of my points for the basis moves to another, it contributes 0 to the character in the reducible representation. Okay? And then when I have sigma v's, notice that sigma v's contain one of those points, and it will remain in place and contribute 1 to the character, but the other two exchange. So I have the representation 3, 0, 1, which is reducible. It's not one of the IRs of the point group C3V. Okay? So we need to work through the reduction formula using the irreducible representations. Those are the characters. So if we check for A1s, we have 1 times 3 times 1 plus 1 times 0 times 2 plus 1 times 1 times 3 equals 6. Divide by the order of the group. I have 6 symmetry operations grouped together in classes. The order is 6. 6 over 6 equals 1. Let's say 6 over h. So we have one of these. It's possible that you can have more than one of the irreducible representations within a reducible representation. So far, we've only worked out examples where there's just one. All right? So then we go to A2. If there are any A2s, they're either 0 or 2 because the dimensionality needs to go to 3. So we check for A2s. You have 1 times 3 times 1 plus 1 times 0 times 2 plus, now it's minus 1 times 1 times 3. So that equals 0. There are no A2s, which means there must be an E to get the dimensionality of 3. So we have 2 times 3 times 1 plus minus 1, 0, 2 plus 0, 1, 3. And that equals 6. 6 over h equals 1. So I have an E representation. So this reducible representation that we constructed using the 3 points here as a basis is equal to A1 plus E.
Shouldn't it be like 3?
Should what be 3?
A plus E, A1 plus E.
Yep. So we have 2 dimension plus a 1 dimension equals a 3 dimension.
Do we need to check for B1 and B2? Or why did it check for B1 and B2?
Those are all of the irreducible representations in C3V, so we're finished. If there were any further irreducible representations, you could check and confirm that there weren't any others that contribute to this IR. But there are only 3 IRs in the point group C through B, so we finished the problem in that regard. Okay. Now let's work out a bigger example. So let's take a cube now. What's the point group of a cube? Close, but not octahedral. So TD, in that point group, notice that there's not inversion. But a cube does have an inversion center. And in essence, if you take TD with inversion, you should get OH. Does that make sense? OH is a big point group, right? But you can do this work with larger point groups, and it's okay. Let's go to OH. And you can follow along in your character tables as I go along. And make sure I don't make a mistake. I make mistakes. That's what I do. And we learn from our mistakes. Okay. So we have EAC3, 6C2, 6C4, 3 C2s that are equal to the C24. All right, inversion, 6 S4, 8 S6s, and then we have the 3 sigma H and 6 sigma D. A lot of symmetry operations. The order of the group, 48. 48 symmetry operations grouped into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. I will not ask you to derive the irreducible representations for this point group on an exam. I would not want to do that. But I will ask you to use this point group and a character table from this point group, for example, or maybe another point group, to decompose irreducible representations. Okay? So what will be our basis for constructing a representation in the point group OH? Let's just take the corners of the cube. So we have these 8 corners, 8 points. We'll call it corners. So we have an 8-dimensional representation that we will construct. And notice in your character table, there are no 8-dimensional irreducible representations. So we know that we have some work to do to decompose this. But first, we need the characters for this reducible representation. Okay? So let's look at the C3s, and we orient the cube so that we look through 2 opposite corners, right? And if I look through these 2, for example, and we've seen this before, two of the corners are aligned with the C3, right? So those 2 opposite corners that are in the C3, those points will remain in place. But the other 6 points, they move around, and they contribute 0 to the character. They contribute off-diagonal terms in the transformation matrix. So the character is 2. Does that make sense? Yep. Okay, let's go through that again. So I have 8 C3 symmetry operations, and those come from 4 C3 axes in this point group. Any one of those C3 axes will pass through 2 opposite corners of that cube. And since I have 8 corners and 2 points in each C3, that's how you get 4 C3s. But for each C3, I can go clockwise, counterclockwise. That generates 8 operations. So what I'm going to do is just pick one of the C3 axes and just do one C3 symmetry operation. And I decided to pick the C3 that passes like this. I could pick any of them. If I pick this C3 and I redraw the view, so I'm looking through that C3 axis, I notice, first of all, that this point and this point are in the C3. So no matter how much I spin it, those points stay in place. And because of that, they will each contribute 1 to the character. So I get 1 to the character from this point, 1 to the character from this point. The other points that are on these other corners, they'll move 120 degrees to some other point. This one here, this one here, this one here, and so on, right? They all move to some other point. So in the transformation matrix, in other words, when I write that out, I will have a 0 term on the diagonal. I'll have a 1 somewhere else. And so they don't contribute anything to the character. Or just qualitatively, I can see this point moves to some other point. It's not going to contribute to the character. It contributes 0 to the character. All right, so I only have 2 points that contribute 1 to the character each, and the other 6 that contribute 0 to the character, and that gets me the value 2 here in this reducible representation. All right? Does everybody kind of get it? And you'll work through examples and learn how to figure this out on your own. And when you get stuck on something, just ask questions. Either ask your classmates, me, so you can work it out and not get stuck on it. Because there is an answer. You'll get there. And once you start seeing it, it will sort of click into place in your mind. Okay, we can go to these C2s now. I don't have to work out any other of the C3s because I know by the rules of theory that all of the characters within a class are the same. So if you work it out for one, you worked it for all of them. The C2s go from opposite edge to opposite edge through those centers of the edges. So here, for example, might be a C2. Okay. There's 12 edges on the cube, 2 opposite edges per C2, so there should be 6 C2s, right? You'll notice that no points are contained on the C2. If I draw the cube looking through the C2, add a little bit of perspective there, right? The C2 passes through here. Every other point on the cube then spins around to another point, another corner on the cube. So that means the character here is 0. No point remains on its original position. Okay? If I look at the C4s, C4s pass through the center and any opposite faces to their centers. Notice with the C4, the points always move to another point. They never move onto itself. So again, the character is 0. If I take a C2, coincident with the C4, I see the same thing. Every point moves to another point on the cube. So again, the character is 0 here. With inversion, every point must invert to another point on the cube. So the character here is 0. For an S4, the character is also 0 because every point will move by 90-degree rotation about an axis, followed by reflection. It moves to another point. And the character here will also be 0. If I go back to my S6, when viewed through the C3, I can go back to this drawing. Notice 2 of the corners are aligned with the S6. But an S6 is a 60-degree rotation followed by reflection about the plane perpendicular. So even though these 2 points are on the S6, they will end up exchanging positions. So none of the points remains in their original position after an S6, and the character goes to 0. Okay? My 3 sigma h planes are the xz, yz, xy planes. They split the cube in half, and the points, any set of 4 points reflects to the other set of 4 points. They all move to another point. The character here is also 0. But for the sigma d, sigma d's contain the C2s. They contain 2 opposite edges of the cube. 12 edges divided by 2 opposite edges per sigma d. There's 6 sigma d's. So if I look at the cube like this, I'm looking through a sigma d perpendicular to the plane of the board. Right? 4 points are contained in the sigma d. 4 points exchange to another point and contribute nothing to the character, but the 4 points in the sigma d contribute 1 to the character. So I have a 4 here, right? And now I have the characters of my representation. I need to deconstruct the representation. So it can take some work because we have 10 irreducible representations to check. So the first one is A1G. All the characters are 1s. And here you just want to be careful not to make any simple arithmetic mistakes by working too quickly, which is something I tend to do sometimes because I'm trying to get through the problem, but just be careful. So for the A1G representation, this is G because the character under the inversion class is positive, 1, which means this is symmetric with respect to inversion. If the character is -1 under I, then this gets the symbol U, which means it's asymmetric or antisymmetric with respect to inversion. That's just a side note. Now if I work this reduction formula out, I have 8 times 1 times 1 plus 1 times 2 times 8. So instead of writing those out, unless you want me to, this is equal to 8. This is equal to 16. This is 0, 0, 0, 0. The zeros are good, right? They save us a lot of time. Plus 12. I guess I missed something, right? Because it doesn't add up. 24. See? Case in point. Going too fast, you get sloppy. All right. So now I add that together, I get 48. Divide by H equals 1. So I found an A1G IR in this irreducible representation. But I have more work to do because I have 8 dimensions to account for. So then we just go down the list. A2G we have the characters 1, 1, minus 1, minus 1, 1, 1, minus 1, 1, 1, minus 1. Now really, the only classes we're concerned with are the non-zero values, where we see non-zero values for the reducible representation. We can just skip through all those classes because they have a zero term. So here we see 8 plus 16 minus 24 equals 0. So there are no A2Gs in the representation. Does that make sense? And then if you wanted to save yourself some time, you could just write whatever characters appear under the three symmetry classes where we have non-zero values in our reducible representation, instead of writing everything out. So the next irreducible representation would be EG. So the characters under E are 2, under 8C3 it's minus 1, and then under the 6 sigma D it's 0. So we get 16 minus 16 equals 0. So there are no EG IRs. And if I'm going too fast, just stop me. Then we have a T1G, irreducible representation to check. The character under E is 3, under 8C3 is 0, and under 6 sigma D is minus 1. So you get plus 24 minus 24. There are no T1Gs. If I go to T2G, the characters here would be 3, 0, and then plus 1 over here. And now, when I multiply this out, 3 times 8 times 1 is 24, plus 1 times 4 times 6 is 24. I get 48. Divide by the order of the group. So there is a T1 or T2G irreducible representation that we found. We go to A1U. We see the characters under E and 8C3 are 1, and under the sigma D, it's minus 1. So as you guess, these will cancel out because we have 8 plus 16 minus 24 equals 0. So then we go to A2U next. The characters here are 1, 1, and then under sigma D, it's plus 1. And now we find that there is an A2U irreducible representation within our reducible representation. So we're up to 5 dimensions out of the 8 we need to account for. So we're getting there. If we go to EU, the characters are 2, minus 1, and then 0 over here. So that gets you 16 minus 16, 0. So there are no EUs. So that means there has to be one of the TU representations in here. Is it T1U or T2U? Let's check. And both T1U and T2U have characters of 3 and 0 under E and 8C3. You only need to look at the character under the sigma D to determine which one contributes to the reducible representation. So this gives you plus 24. So we need a plus 1 here. That's the T1U irreducible representation. So that equals. All right. So now we've learn how to use different point groups. So now you see why it's going to be so important to assign point groups correctly very early on. Because if we have the wrong point group here, we cannot arrive at a correct solution. Once you have the point groups, we need to be very familiar with the symmetry operation so that we can derive the characters, first of all, the reducible representation, either based on kind of looking at it and assigning values, or more rigorously using transformation matrices. Once you have the characters of your reducible representation, we go through the work of using the reduction formula to find all of the irreducible representations that make up the reducible representation. We will be doing that throughout the semester for all sorts of different problems. So you'll want to become very good at doing this over the next week so that we can apply this down the road. Yep.
Have some kind of, let's say, practical meaning?
Yes, they have very practical uses and meanings. I haven't shown you that yet. I've given you some hints, but that will be the subject of the second half of the remaining 2/3 of the book.
It means therefore that for each particular point group, you have some special letters you use.
Special letters?
Because this is the first time we are using the T2D, T1D, and A1D.
Yes. So the A's and the B's, as we've already discussed, those refer to one-dimensional representations. The E's always represent two-dimensional, and T's always represent three-dimensional. The 1s and 2s are just ranking based on usually the character under the sigma H in this case, or otherwise some mirror plane in the system. And then the G and U are designations with respect to inversion. If it's a +1 character under inversion, it's a G. If it's a -1 character under inversion, it's U. And if you look at the point group OH, and if you look at the character table, notice all of the irreducible representations are sort of split. So all of the G representations are in the top half. And look at the character for inversion, it's positive, +1, 2, or 3, based on the dimensionality of the representation. The bottom half of that character table, you have all of the IRs that are U in symmetry, Ungerad, and the character under inversion is always negative, -1, -2, or -3, depending on the dimensionality of the irreducible representation. So you can look for that in your character tables. Okay. Yeah, the only other notations really to think about would be primes. Sometimes you see rotational axes, particularly in D point groups where you have a prime. That would indicate something like a dihedral type aligned C2 versus one that's aligned with vertical planes. And then we went through the idea of sigma D versus sigma V. In all cases, those are vertical planes oriented along the principal axis. They contain the principal axis, but the sigma V's would generally be called the sigma V's versus sigma D's have to do with whether they contain the C2s that are perpendicular to the principal axis. So if the vertical planes bisect angles formed by the C2s, then it's a sigma D. Otherwise, if they contain the C2s, it's a sigma V. And I think that's all of the different notations that you'll see for the point groups. At this point, don't worry about notations for the infinity point groups. I'm not going to test you on that. I don't think I even understand it, to be honest. And then the only other kind of oddball, at least in terms of your character tables, you could certainly have higher dimensional point groups, but if you look at the icosahedral point group, which does come up from time to time, not too frequently, but we have a character table for the point group IH, you'll notice that there's some irreducible representations with a dimensionality of 4 and 5, right? And those have the letters G and H. That's not something I'll test you on. Once you're working with the icosahedral IH point group, you just go to the character table. You understand how it works at that point. Okay? So I think that's a good stopping point.